Now let's discuss rate laws and how to write them. So rate laws have been determined for a large number of chemical reactions, and they are always determined by doing a bunch of highly controlled experiments to try to figure out what the reaction rate is and what it depends on in terms of concentration of reactants. So let's take a very simple reaction where A goes to products. A is just our reactant. For that very simple reaction, the general form of the rate law is that the rate is going to be equal to the specific rate constant K times the concentration of the reactant raised to some power. I'm going to call that power N. Now, little n is the thing that we need to figure out when we write down a rate law. N is the order of the reaction. It can be a whole number or it can be a fraction. You must determine it experimentally. The only way to figure it out is to do a bunch of highly controlled experiments. It is not necessarily related to the stoichiometry of the reaction, although it may appear to be related to the stoichiometry of the reaction, as you're going to see. That is not what determines the order of the reaction. If you have more than one reactant, you have more than one reaction order involved in the reaction. So for more than one reactant, for example, let's take if I have A of A plus B of B going to products. Okay, so that's just giving you the idea that I have two reactants involved rather than just one. The rate law might involve both of their concentrations. So the rate law would be equal to the rate constant times the concentration of one of the reactants raised to some power, I'll call it N, times the concentration of the other reactant raised to some other power, I will call it M. So the reaction order is given from both of those, and you would get the overall reaction order by summing them. So M plus N would tell you the overall reaction order. Okay, so this might not make much sense until we do an example. I want to do an example, but before I do it, I really want to emphasize one more time that reaction orders are not related to the stoichiometry of the reaction. They may appear to be, but that is not what determines reaction order. Reaction orders are determined simply by the mechanistic pathway, how bonds in the reactants are being broken and how new bonds are being formed to make the products. And the only way to figure out the reaction orders, the numerical values of the reaction orders, is to look at experimental data. So now I want to do an example where we take an experimental data set and we calculate the reaction orders for that reaction. So let's write the rate law for the reaction where two nitrogen monoxides react with bromine to make two NOBRs. Okay, so this is the reaction that we're dealing with here, given the following experimental data. Okay, so here I'm giving you an experimental data set. I'll zoom out a little bit so you can write it down. You might want to pause here so you can write down all of this experimental data. 5 experiments were done running this reaction with different initial concentrations of each of the reactants, the NO and the Br2. So you'll notice in some of them, the NO was held constant while the concentration of the other one, the Br2, varied. And in others, the concentration of the bromine was held constant while the concentration of the NO was varied. So that is the key to doing a successful kinetic experiment. When you have two reactants, you want to hold the concentration of one of them constant while you vary the other one and vice versa so that you can tease out the dependence of the rate on the concentrations of the various reactants. Then, for each of these scenarios, the rate of the reaction in moles per liter per second was measured. So these are the data for each of the experiments that was done with the varying concentrations of the reactants here. So when you're given a problem like this, your job is to write the rate law. And what they mean by that is this. The rate of this reaction is going to be equal to some rate constant K times the concentration of one of the reactants raised to some power. We don't know what it is yet. I'm just going to call it M, times the concentration of the other reactant raised to some other power. Pardon me. Your job when you write down a rate law is to figure out what M and N are. Okay, so your job is to use the data to calculate the reaction orders. That's what is meant when you are asked to figure out a rate law. So if we want to figure out the dependence on bromine, so if we want to calculate N here, we want to look for two experiments where bromine concentration is changing, but the NO remains the same. Okay, so to figure out the dependence on bromine, so to figure out the dependence of the rate on the concentration of bromine, you look for two experiments where the bromine concentration changes while the concentration of the other reactant, what is it? The NO concentration remains constant. Okay, that is how you can calculate the value for N, the order for the bromine. So looking here, I can see that in experiments 1 and 2, I have a situation where the bromine concentration changes while the NO remains the same. That's key because what you want to do is set up a ratio where you take the rate that is determined for one of those. Let me zoom this out so you can kind of see what I'm talking about here. The rate for experiment 2, and you want to put that over the rate for experiment 1. Okay, the rate for experiment 1. The reason I want to do that is because I can set up a situation where I can cancel out everything except bromine, because the rate comes from this relationship here, right, that I just wrote. So I can plug that in, that K times the NO concentration for experiment 2 raised to the M power times the bromine concentration for experiment 2 raised to the N power, all over the same thing for experiment 1. So K times NO for experiment 1 raised to the M power times the bromine concentration for experiment 1 raised to the N power. Now, the reason I did that is because I made a choice so that the NO values are going to be the same for experiment 1 and 2. And that means that what I can do down here is cancel those because they're going to be the same. K is a rate constant, so I can cancel K as well. So this clever selection of two different experiments enables me to basically set up the data so I am using the rates. So rate of experiment 2 is going to be 24 moles per liter per second. Rate of experiment 1 is 12 moles per liter per second. So I can put that in here, 24 moles per liter per second over 12 moles per liter per second. That's the rate of experiment 2 over the rate of experiment 1. And that's going to be equal to the bromine concentration in experiment 2 over the bromine concentration in experiment 1. And I'm going to have them both raised to the power of N. So I can put this whole thing in parentheses and raise it to the power of N. And that last bit I got just from this after canceling out the other stuff. And I have those actual values for the bromine concentration. I have them here in my table, 0.1 and 0.2 molar respectively. So that means that I can really simplify this. 24 divided by 12 is 2, and I'm going to have 0.20 molar divided by 0.10 molar for those concentrations raised to the n power. So now I can solve for n. This simplifies to 2 being equal to 2 raised to the n power. And from there, it should be pretty obvious that n is equal to 1. So we would say that the reaction is first order in bromine concentration. That's what we just figured out here. If you have something more complicated, it might not be obvious what n is. So just to remind you how to pull the variable out from the exponent, you can solve it by putting a natural log in front of each side. So the natural log of 2 would be equal to the natural log of 2 raised to the n power. And that means that you can say that the natural log of 2 equals n ln 2. You can basically pull the exponent out in front of the natural log, and then you can solve natural log of 2 over natural log of 2 is going to be equal to n, which of course is going to be equal to 1. Okay, so if you have something more complicated, that is just a reminder on how to pull the variable out of the exponent. So we figured out that n equals 1 and the reaction is first order in bromine. So I'm really only halfway there because I need to go back to my rate. I figured out what n was. Now I need to figure out what m is, what the order is for NO. So there, the trick is going to be to find 2 experiments where NO changes while the bromine is held constant. So let's find 2 experiments where bromine's held constant, but NO is changing. So it looks to me like experiments 4 and 5 are going to do the trick there. So for experiments 4 and 5, I have the rates, and I have bromine being held constant while the NO concentration is changing. So I can do the same kind of setup. I can do a setup, and this, once again, I want to emphasize that I'm doing this to solve for the reaction order of NO, okay, which I called M. I'm going to take the rate of experiment 5 over the rate of experiment 4, and I could have reversed them. It doesn't matter which one I put over the other. And that is going to be equal to K times the NO of experiment 5 raised to the M power times bromine for experiment 5 raised to the n power, but I know now that n is equal to 1 over, and I'll just put the n here in case I don't want anybody to get confused when you look back over this, over the same thing for experiment 4. So the concentration of each reactant for experiment 4 raised to their respective reaction orders. And once again, here I purposely chose 2 experiments where I can cancel out the bromine concentrations because I'm holding them constant. And once again, I can cancel out the rate constant because it is just that, a constant. So this simplifies to the rates for those experiments. Let me look them up in my data table. The rates for those experiments were 108 and 48 for 5 and 4 respectively. So I'm going to plug those in for the rates. 108 moles per liter per second divided by 48 moles per liter per second is going to be equal to the concentration of NO for the 5th experiment over the concentration of NO for the 4th experiment raised to the power of M. And now I can plug in my values for those. So 108 divided by 48 is going to be equal to 0.30 molar divided by 0.20 molar. Those are just the molar concentrations from my data table raised to the power of M. And if you do the simplification and use natural logs, You can solve for m, and you find out that m is equal to 2. And this tells us that the reaction is second order in terms of the concentration of nitrogen monoxide. So that means that the rate law in the problem can be written as the rate being equal to K times the concentration of NO squared times the concentration of bromine, and that's raised to the power of 1. So this is the answer to the question of what the rate law for this reaction is. What I needed to do is figure out what those exponents were, and it's second order in NO and first order in bromine. So that is how you write a rate law. Now, as a follow-up question, you may be asked to calculate the specific rate constant. And for that, you can take any experiment you want. Let's take experiment number 1. I'm going to go back to my data table to find the data for experiment 1. So for experiment 1, I have a rate of 12 moles per liter per second, and I have concentrations of 0.1 molar for each of those 2 concentrations. So I can plug in all of that data to calculate K. So for experiment 1, the rate is 12 moles per liter per second, and that's going to be equal to, I'm plugging this literally into the rate law that I just calculated. That's going to be equal to K times 0.10 molar squared times 0.10 molar, because that was the concentration of NO and the concentration of bromine. So you can do the math and collect all of the numbers on one side to solve for K. And it turns out that K for this reaction is equal to 1.2 times 10 to the 4. And the units I have to get from doing the math, the units are really going to depend on the reaction order here. So if you notice, what's going to happen here is that one of the molarities is going to cancel, but then I'm still going to have the other 2. And I'm going to end up with the reciprocal of that kind of squared molarity. So it's going to be liter squared over mole squared seconds. This is going to be the value for the rate constant for this reaction, and you should get the same value regardless of which experiment you choose to calculate it. Okay, so the last thing I really want to emphasize here, very important, the units of the specific rate constant, the units of K are going to vary depending on your reaction orders. So the units of K depend on the reaction order. So you have to figure them out for each individual reaction that you're dealing with.